Okay, let's get started. Welcome everyone to a course on life in the universe, which is probably not the usual course you're taking here at UCSC. This is a course that we started about 2 years ago, and as you see in a moment, it's aimed at sort of bridging quite a few of the different science disciplines into one study, and actually really one question, and the question is there life elsewhere on Earth, and where did life on Earth itself come from as well? So I guess 2 questions. So just to tell you a little bit about myself, I'm a professor here at UCSD. I'm an astrophysicist. I live just down the hallway down here, and so when I have office hours, which we'll schedule later on in the lecture, that's where they'll be. There's my email address. It's up on the webpage. I'm an observational astrophysicist, so I actually go out and use big telescopes. So this is actually a picture of me sitting in front of one of the instruments I built here. For the Magellan telescope, which is this telescope right here. This is about 6.5 meters across. It's a little hard to tell how big that is because I'm way in the foreground. But 6.5 meters, anybody know what that is in feet? No quick foot-to-meter converters here? 20 feet. About 20 feet, good, yeah. 20 feet wide piece of glass. This is actually not the largest telescope that we use for our research, but it's a pretty big one. And this instrument I built about 6-7 years ago, and that cost about $2 million to build. And it's hanging over my head, which is very fun. The reason I'm interested in teaching this course is because the objects that I study, which are very cool stars, things called brown dwarfs, which at some point I may talk about a little bit, and in particular extrasolar planets, which are things we'll definitely talk about quite a bit, are objects that I study. I study their atmospheres using spectroscopy. And one of the techniques we'll talk about in looking for life out in the universe is using spectroscopy to see if we can see the signatures of life on other worlds. So this is what the course is about. Are we alone in the universe? Is life on Earth all the life that there is? And we're going to talk about this much more broadly. You've probably heard of this question before in the context of looking for intelligent life in the universe. There's just a New York Times article, which we'll talk about in just a moment, about the SETI project, which is looking for intelligent life, looking for signals from intelligent life in the universe. But the sort of study of astrobiology encompasses all kinds of life that's in the universe. And so we'll talk not just about little alien green men, but also little bugs that happen to be on other planets, if they're there. This is not an old question. Epicurus and ancient Greek Epicurus actually asked this similar question back in 300 BC. This is at a time when the stars were the main attraction in the sky. There wasn't much in terms of YouTube on. Night sky was pretty dark. This is Greece, so it's nice and clear. And so a lot of Greek philosophers spent a lot of their understanding on night sky. And Epicurus, into a letter to Herodotus, actually commented that there are infinite worlds both like and unlike this world of ours, which he speculated he didn't know. And we must believe that all these worlds are living creatures and plants and other things we see in this world. That's a pretty modern statement to say back in 300 BC, when nobody knew what the stars were, nobody knew what the planets were. But at least this particular Greek, and also Pythagoreans and other groups of Greeks, imagined that there are actually probably other places that had life just like Earth. That kind of died out for a while, but in the sort of 15th and 16th century, this idea became more popular again. This is a statue that's in Florence, Italy. Near Florence, Italy, of Giordano Bruno. Anybody heard of Giordano Bruno before? All these like ancient people's names, yeah. So if you're a scientist, Giordano Bruno is often sort of put up as the scientist martyr. He was actually burned at the stake in 1600, which is a lot worse than, say, getting your paper rejected or defended or something like that. And partly the reason he got excommunicated severely was because he had what the church thought were very crazy ideas about the universe and about existence. And he had said something like this, very similar to Epicurus, that there are countless suns, countless Earths, all rotating around their suns in exactly the same way as the 7 planets in the solar system, so they didn't know all the planets yet. It is utterly unreasonable to suppose that those teeming worlds should be uninhabited and should not bear similar or more perfect inhabitants than on Earth. So I'm trying to emphasize that this is not an old question. This is a question that's been asked by many, many different people over the years. When you get up into the 20th century, things get a little more fun because now folks have telescopes and they can go out and look at things like Mars, and you get all sorts of alien encounters, landings. This is actually from 1909. Percival Lowell was a very wealthy person who lived out in Arizona. In fact, there's a Lowell Observatory that's named after him, mostly because of his money, not because necessarily of science. And he made a big splash in the early 20th century because he believed he saw canals on Mars. Now, as we'll talk about a little bit later, what he probably saw were the veins and arteries in his eyeballs, which is not exactly the same as canals on Mars. But this was a big splash that we believe that there was actual inhabitants and even civilizations on the closest planet to the Earth. And this spilled out into popular media. You probably heard the story of the War of Worlds. Maybe you've heard of the radio broadcast that happened in the 1930s. Well, the book itself was written back in 1898, and even before Lowell's maps were made. And it talked about Martian, civilizations coming to invade us. You see sort of the first evidence of aliens with hostile intents. Although, in fact, books have been written about aliens way before this. Kepler, back in the 15th century, wrote a story about visiting the moon and visiting the aliens there. This is a great old movie. I really encourage you to take a look at it. It's a 12-minute movie on YouTube. It's really fun. It's a silent movie, 1902, very, very early on. But many of the early movies back in the silent age were kind of science fiction stories because you could make these really extravagant settings and plots, and you didn't have to speak, so that's even better. And in fact, in this one, they go off and they take a rocket that somehow pokes an eye in the moon, bring back a whole bunch of aliens, and it's all great fun. So there's this idea in popular media, of course, has been around even to today. I mean, most of the television shows, many of the movies that we see, have some kind of science fiction and often some kind of alien element to it. Many of the popular ones are. So this hasn't gone away for a while. So why is this such an interesting thing now? I mean, people have been thinking about it for hundreds of years. Why do we care now? Well, it's not until really the last kind of 50 years that we've been actually able to scientifically start probing this question, whether there's actually life off the Earth. One of the earliest earliest tactics of this was the Viking Lander. This is a picture of Carl Sagan, who, anybody have heard the name Carl Sagan before? So he's a very popular science popularizer, not alive anymore. This is him standing not next to the Mars rover on Mars, but Mars rover actually, I think that's out in the Mojave Desert. And this is a picture of the Viking on Mars itself. And one of the main experiments that this landing instrument did was to look for life on our closest planet. Now, we had known before Viking landed that there weren't canals on Mars, there weren't massive civilizations, that Mars looked pretty dead. But you still don't quite know if perhaps there's microscopic life underneath the soil. And in fact, that's still a question that people ask today. But Viking's experiments were actually inconclusive, which is actually interesting because it wasn't disproven that there's no life. It wasn't proven there was life. It was inconclusive. And so this is why people still study the Mars system. And we'll talk about other reasons why Mars is interesting for the possibilities of life. So all of the experiments we've done so far lead us to one conclusion, that the only place in the universe where we know for sure life is, I'm pretty sure, is where we are right now on this one planet Earth. And the sort of field of astrobiology has grown out of trying to understand why that would be the case, and actually maybe it's not the case, and how do we find life forms on other planets? How common is it for life to spring up? If Earth is the only place that you could have life, what is so special about Earth? And if Earth is not that special, then what other forms of life could there be in other planets? So just to kind of get our heads rolling on this, you should have a sheet of paper. If you don't, anybody know where the pile is? Okay, can you start distributing them back? Because I think we had some late folks come in. Grab one of these sheets. And I want you to take just 5 minutes to write down your thoughts. All right, you right now are the expert, what do you say this? The expert novice in this class, all right? When the future you looks back and sees what the past you were thinking about this class, they can look back at this writing and see it. They're coming around right now. Can you pass them over on this side as well? So take 5 minutes and just answer this question. Do you think there's life in the universe beyond the Earth, and why or why not? Okay, who needs more time? Okay, so now I want you to turn to your neighbor and kind of discuss your answer with each other. See if you come to similar conclusions, see if you come to different conclusions, and try to sort of flesh out why you might have different ideas. Take about 3 minutes for this.
I just said that there's, I would think that the requirements are like really complex, but just there's more statistics. Yes. There's just so many, like, I know I said it, really specific categories in our life, because of they just has like statistics, I would think that there has to be another place that's similar. Or maybe it's not, I don't know, that's how I just think it's like statistics, yeah, what you say. I agree. No, I want actually the image where you show Tommy Desert. Yeah. Oh, cool.
If you've exhausted your conversation with your neighbor, find another neighbor so you've got a different answer than that.
Yeah.
Spread it out a little bit more. We got about one more minute.
And then he puts me on our galaxy and show the stars and all that.
Okay, I'd like to have 3 people share their ideas. 3 people. 1, 2, 3. Go ahead.
I think life is probably out there, just considering kind of the near infinite possibilities of planetary systems out there, and just considering the number of stars in the universe, which is probably infinite. There has to be one. Although whether or not we'll ever find that life is a different question.
Okay. Okay. Any comments on that? Did ever people have other sort of ideas about there's just so many stars out there? That... Do you have a comment?
Oh, well, basically, from what I've learned, I know there's a lot of other stars, just like the sun. So to me, that gives the possibility of a lot of other planets, just like Earth, with the conditions for life.
Mm-hmm.
So.
Okay. In the back.
I can't add too much to what they were saying because pretty much what we came to.
Okay.
But in addition to like conditions of Earth, we have some house life under different conditions.
So life in a non-Earth-like environment might be possible.
Yeah, because there's like Earth-like environments where it's like under the ocean, you see trenches where there's life.
Mm-hmm.
So there's stuff like that out there. And, you know,
okay.
It's more likely that there's something out there that there's not.
Okay. All right. So good probability. Good,
Yes.
Good numbers, good probability. Okay. Do you have anything to add?
Yes, I think there's life in the universe. It's just that, like, because I once heard that, like, the universe is like expanding. Like, it's like it's still expanding, and we don't know how like, I don't know. We don't know if there's no limit to that.
Mm-hmm.
And I just kind of think that it's in terms of like our own galaxy. I think we haven't talked about it yet, but the galaxy in our galaxy is just like a certain amount of planet, but like beyond our galaxy, there are more stars or like the planets that we haven't encountered yet, I guess.
Mm-hmm.
So I think there is. It's just we haven't encountered it.
Okay. Right. Did anybody have a? Because those are all 3 of those are very positive takes on life in the universe. Does anybody have anybody think there is no other life in the universe? Wow. Positive.
You probably wouldn't take this class if they didn't.
Well, you know, I mean, a good skeptical student could take a class and say it's totally bunk. And I should make sure to be clear that, you know, this class isn't about, hey, there's life out in the universe and we're going to find it. It's actually still in that question, is there life? Because we still haven't found it. We don't have evidence yet of life off the Earth. And so I don't think you know, we're all seem very positive in terms of our opinions, but I think at this point, even the scientists, this is still an opinion. We don't really know whether that's the case or not. So there's a lot of discussion about planets, life around other stars. What about and did any of you discuss life off the Earth, but maybe more locally in the solar system? Anyone comment on that? Yeah.
I was thinking like Europa is a possibility. There's water, sort of like inside. That's Europa is the moon of Jupiter, I think.
Mm-hmm. Yeah. Okay, so so just because there's water, okay. So if there's water, there may be life. Is that kind of the okay? Any comments on that? Can you think of places where there's water but no life? I guess we don't know. Okay. All right. So many things you just commented on are things we're going to be touching on. The idea of what kind of chemical requirements there are for life. What are sort of the possibilities in terms of just numbers? Where can life be depending on the sort of different conditions? And so keep these ideas in mind because we're going to be revisiting these a couple times. And hopefully we'll get a little more details on sort of these ideas as we go along. Now, just to put a word to it, so I've mentioned this word astrobiology. I just want to make sure it's clear that this is a subject. All right, this is a field of study. Astro, universe, life biology. So this is the study of life in the universe. It's a fairly new field of research, fairly new being like 50 years, which doesn't seem very new, but compare that to stuff like chemistry and physics and stuff like that, it's pretty new. And it covers quite a wide range of different topics, as I mentioned. So it's a scientific life of, say, in its past, present, future. So this is a pretty broad subject. Everything we know in all time, when it regards to life, is sort of the field of astrobiology. And you think about it, biology is actually a much more confined sense of study because that's focused primarily on life here on Earth. Whereas astrobiology is looking at life at a much broader range, both in time and space. It wants to address sort of three pretty big questions that's also at the foundation of biology itself. How does life begin and develop? Not just here on Earth, but potentially in other worlds. Does life exist elsewhere in the universe? Right? How do we go about looking for that life? And what's the future of life here on Earth and beyond? Right? As we'll talk about the idea, you've probably heard of mass extinctions, wiping out the dinosaurs, stuff like that. That's a fairly new idea and sort of the gestalt of our understanding of the history of the Earth. And so we can also start to look forward and see what is the future of life here on Earth, not just what do we see in the past. And as I mentioned, this is interdisciplinary science, and it really covers quite a lot of different fields, which I believe here, right? So, and we'll talk about all of these things. And importantly, it also impacts other fields that are not necessarily scientific. And so we've already given some examples of the idea of life off the Earth in terms of art, in terms of film. It also impacts philosophy. It obviously has a very big impact on religion, right? If we think about, the sort of human-based religions, what happens if we have an alien culture? Do they have the same God, right? Do they worship the same sort of ideals? That's, something that we don't have to worry about because we don't know any aliens yet, but perhaps someday we may have to think about that. And of course, it also impacts culture. The picture I showed of the sort of newspaper article of Lowell finding canals on Mars had a huge imprint on the culture of the early 20th century. It's part of the driver of sort of the, sort of fear of mechanized sort of nations. That Martian landing was really kind of an analogy of sort of the industrial nations becoming much more aggressive and militaristic. And so we have a backlash of sort of a connection between the culture of today and what we imprint that on the aliens that we think about, and how those alien ideas or alien stories manifest themselves back into our perception of the culture around us. Right? Science fiction as a field is really about what's going on in the world around us. It may seem like it's this futurist, fantastic, amazing, like crazy things going on, but at its heart, it's really a commentary on what's happening in society today. And so there are major feedbacks between now understanding if really these kind of ideas, these fantastic ideas are true, whether there is life on other planets, and what kind of life there is, and how we deal with the culture here on Earth. Now, in terms of these intersections, the three things we'll talk about the most in this class are going to be biology, geology, and astronomy. So when we talk about biology, obviously biology is in the word astrobiology, so biology is going to be a pretty big important part of this. How many of you are some kind of biology or life science majors here in this class? Wow. Okay, very few. Don't be shy. It's okay. Usually I have a whole bunch. Good. So I can talk about biology, not be embarrassed when I only know an astronomer's worth of biology. But obviously this is a process of organizing systems, living systems as we know them today, as we know them here on Earth. And so the biology aspects of this program is seek to understand the origin of life here on Earth, right? From the basic chemicals that we now know could be delivered to Earth from astrophysical means. Right? They don't have to be generated by life systems. But how do we go from very basic chemicals to the very complex chemicals systems that are walking around and sitting in this classroom today? It provides an idea of evolution and diversity, which is going to be a very important factor in how we get from these very small chemicals to, again, sort of walking, talking life forms we see today. And it's taught us how microbial life can survive in a very wide range of conditions. So this goes back to the extreme cases that you mentioned before. Where life can actually exist even here on Earth is a fairly broad range. And how do biological systems manage that? And then how is the interaction with life and its environment? We'll see lots of cases where the sort of emergence of life or the change of life has had a humongous impact on the climate of the Earth. In fact, the reason that I'm sure you may know this, the reason we have oxygen in this room today is because of bacteria back in the sort of 3 or 4 billion years ago, right? We should have very little oxygen. In fact, if you look at Mars and Venus, they have essentially no oxygen in their atmospheres. So just life forms have changed dramatically the atmospheric composition of the Earth, and that's changed all sorts of other aspects of the geology of the Earth as well. So the feedback between biology and astrobiology. Planetary science encompasses study of planets. I'm not going to go through these in great detail, but again, talking about sort of the connection between what we understand about planets, how they form, what kind of geological processes, atmospheric processes happen in them, and how that connects with life. And then, of course, astronomy is going to be important because if we want to look for life off the Earth, that's looking out into the stars. And so we talk about, for example, where some of the prebiotic precursors, the elements and the molecules that eventually give rise to biological life, at least here on Earth, where they come from astronomically. In fact, it's quite amazing that many of the amino acids, the basic sugars, are actually produced just in space. You don't need a biological system to give you the basic building blocks. And that's been a pretty interesting revelation just in the last few decades. Of course, if we want to find life that lives on planets, we have to look for other planets. And your generation is the first generation in which we know that there are planets outside the solar system. That's a completely new field of research, only 20 years old. And we've been finding thousands of planets and just starting to sort of get into the details of what they look like, what kind of properties they are. So this is a really big boost to being able to do this. And then, of course, if we want to talk about civilizations, then we're starting to talk about cosmic timescales, the idea that the universe is expanding. So what does that play out with the future of life if we go on a really long scale, trillions of years in the future? Will the universe hold life for that long period of time? Or is this just a brief period where life can flourish in our universe? These are all questions that we can answer with astrobiology. All right, now the hard part of this, of course, is what do we mean by life? I keep throwing this word life around, and I'm guessing that many of you probably have different definitions for what a living thing is. And it turns out that even scientists have different definitions for what living things is. And when we look out at life, or we look out at our environment, even here on Earth, it's very hard sometimes to pin some things down to whether they're living things or not living things. So if I go to something like a rock or a crystal to a cat, those are pretty easy things to distinguish. This is from a talk, by the way, that I made. I think I'm going to assign for one of the homework assignments. But there's all sorts of in-between things in this sort of scale of life to non-life to life. Sorry, this is a little fuzzy, but things like viruses. I'm sure you've heard of viruses. I think some of you have them in the room. I hear a lot of coughing. Some aspects of viruses are very lifelike, and we'll talk about what those properties are. But for example, reproduction. Viruses are very good at reproducing themselves. That's part of the problem. All right, they contain DNA, but they don't have some of the other life processes like respiration, like metabolism, that cellular life forms have. There are, sorry, you can't see this at all, but there's another set of molecules called prions. Anyone heard of prions before? The life scientists have. Yeah, okay. So prions are misfolded proteins. They're just chemicals. But in fact, those misfolded proteins can induce other proteins to misfold, and at some level, that's a measure of reproducibility. Those have no, they have no intentions, right? They're not, again, metabolizing or respirating, but they can spread through environments, and they can actually have a very large effect on life forms, including humans. So where we classify things becomes a little bit difficult when we get to some of these special cases. And in fact, it may show us the pathway from basic chemicals to biological systems as we kind of know it today. That's just one path, though, right? That's the one path, the one experiment that we have here on Earth. Whether or not that same experiment happens in other places is another question. Searching for life beyond the Earth actually starts a little closer to home. So again, only one of these planets we know so far has life around it or in it. But in fact, there are other places where we believe in the past the conditions were very, very Earth-like. Right? Mars and Venus at some point in the past had water on its surface, had an atmosphere that was a very similar atmosphere to Earth's atmosphere at the time, like very heavy in carbon dioxide, but that's still a place where life originated on Earth. And so sometime in the past, Mars and Venus may have been teeming with life. We don't know, right? It's been very distant past. We don't see evidence of it today. But it had the conditions, at least as we can tell from our understanding of planetary science and planetary evolution, to have the right things like water on the surface where life can emerge. It turns out there's even more real estate for life, even in our solar system. You mentioned Europa earlier on. So all of these giant planets, Jupiter, Saturn, Uranus, and Neptune, have very large moons around them. In some cases, those moons have more water in their interiors than the Earth has on its surface. And so these may also be places that life can thrive, but perhaps not life in the sense that we see it here on Earth. And we don't know yet because we haven't seen anything like that. We're just starting to send the first probes to do this. All right, so all of us were very positive about this, but why do we think life is likely to exist? Well, as I mentioned, some of the precursors, like these organic molecules, we know can be formed in non-biological processes, and they're quite abundant in the universe. This is a picture of Wild 2, which is a comet that was had a close approach. I think this is back in about 2008, 2009. We just actually landed on another comet. Does anybody know the name of that mission? Or the lander? Ever heard the Pee-wee lander? Yeah, a couple not it. Okay. This is good because I have an assignment that's going to fix all the unknown stuff here. So, but by looking at, so this was actually a sample collection. They actually flew a spacecraft behind the comet and collected some of the material that's coming off that. And that material they brought this sort of canister down back onto the Earth. That crash landed and broke open, so it wasn't that great of a thing. But they were able to collect some of the dust from the comet, and what they found were these two molecules here, methylene and ethylene. Ethylamine. This is why I'm not a biologist. But these are precursors for amino acids in our body, for proteins in our body. Right? These are amino acids or precursor proteins in our body. And they're just sitting around on the comet. Now, maybe the comet is teeming with life. Probably not, because it's not really great conditions for life forms, at least as far as we know them. But these very simple molecules are things that you can form through basic chemistry just on the surface of these objects. And so that's a possibility. We know that planets are very common on other stars. This is not particularly new news, but it is new news for us old folks. The first sort of planets were found back in 1995. I'm not going to ask how old you are when that happened. But now we know over 1,500 definite exoplanets and thousands of more candidates are out there. Most of these are very big, like massive Jupiter-sized planets because those are the easiest ones to find. But we know now getting close to 100 small little terrestrial bodies around other stars. And by extrapolating sort of how well we can detect those things out to what might actually be there, the estimates are that probably one of these little terrestrial bodies around every star in the galaxy. And there's 100 billion stars in the galaxy. It's 100 billion worlds, rocky worlds. Very good, right? So that's very promising and very new. We know that microbial life here on Earth started off very early, right? There are these things called stromatolites down in Western Australia. This is a picture of one of them here. This is just a rock. You just picked it up. But it seems like a very weird rock because it has these sort of layers attached around it. It turns out that these layers are very similar to, there are these bacterial mats that are in the same area and other areas around the Earth. And the bacteria, as they grow, they sort of form these mats, and then the ones on the bottom get kind of pissed off because they're not getting any light, so they move up to the top, and in the process they deposit some of their material waste. And it's these kind of layers that form these rocks, and these rocks have been dated back to about 3.5 billion years ago. That's only about 1 billion years after the Earth itself that we believe is formed. So that kind of evidence suggests that, at least here on Earth, it didn't take that long. 1 billion years is still pretty long, but at least in sort of a ratio of the age of the Earth, it didn't take that long for life to take hold. So if it was easy here on Earth, the question is, would it be easier in other places? At least this very simple forms of life. And finally, this is good back to the comments back here, that we know that life forms can survive in very extreme environments. Here's just a couple of examples. This is at Yellowstone National Park. Who's been to Yellowstone? Have you seen that very colorful kind of these hot springs that have like kind of oranges and greens and stuff like that? That's all life forms. Those are not minerals, those are life forms. And those are very special life forms that can survive in extreme environments. So we call them thermophiles, right? Philes being like, thermo heat, right? So they like heat. And these are bacteria that survive in conditions that if you put human cells in there, they would completely melt away. Right? So somehow these cells are able to survive in those extreme environments. Strip mines are terrible, but if you're a particular type of acidophile, they're wonderful because nothing else can grow in them except you. And so we have these, again, extreme and polluted environments where we find that there are things that are thriving in those regions. There are things that survive in very high metal concentrations. There are things that survive in radioactive areas, right? Some of the areas around, say, nuclear waste dumps or around reactors that have had problems, you still find bacteria that can survive in these extreme environments where, again, other life forms are not able to survive. And so we've been able to find lots of organisms in places where you really wouldn't expect to find them, underground, in the ice. And it suggests that you don't need to have the sort of very nice, warm, perfect, wet conditions for life to actually take root, that perhaps life is a little more robust than that. All right, so all of these things suggest that biology may be common in the universe. It may just not be like Earth's biology, but at least there's some evidence here on Earth that maybe this is not the only experiment that goes on. And so the argument is that the reason we have this class is that we really haven't been much any closer to discovering for real whether there's life around the Earth in the universe, although we still don't know the answer, right? It's still a big if it exists, right? All we have are these tantalizing clues from our one experiment here on Earth. Right? But now we have the tools to go beyond that. All right, any questions on that? This is the big pitch for the class, so any questions on sort of these concepts? You're sold. Okay. All right. All right, so now I'm going to break your heart. I'm going to tell you what we're going to do for the class. So here's what we're actually going to cover in this class, which is a lot. Because if we're talking about an interdisciplinary topic that covers 6 fields of science and impacts all sorts of humanities, this is going to be a pretty dense class, all right? But we'll keep it on a sort of conceptual level. So we're going to be talking about the scientific definition of life. Each of you may have your own definition of what life is, but we actually, as scientists, have sort of more formalized ways of analyzing what life is. Not ways that necessarily everyone agrees upon, but at least sort of the principles that we can approach different subjects, different materials, and figure out whether they're living or not. We'll talk about the origin, geology, climatology of Earth. Any SIO people in here? Scripts? Wow, you got everything. Okay. All right. So I'll be careful when I talk about that. We'll talk about the origin, evolution, and characteristics of life here on Earth. All right. The evidence that we have that life started very early on. The evidence that we have that life has evolved continuously over this period, and sort of the episodes of evolution and mass, sort of extinction events that have happened. And what that can have is in terms of the future impact of life on Earth. We'll talk a little bit about the solar system, because that's sort of our first playground to start looking for life off the Earth. It's nearest places. So we'll talk about the feasibility of life out in different places in the solar system. We'll move out to other stars and other planets. Talk about some of the properties of those planets that we've just now started being able to measure, and whether or not those planets are in regions where they're habitable. And then at the end, we're going to get very speculative and start talking about, is there not just life forms, little bacterial life forms, but is there other more advanced life forms, things that we can talk to? How would we talk to them? Are they talking at us? Are we listening? And even if they're not there, is there any way that we could become those aliens and spread out in the galaxy? What limitations do we have for this? So this is getting into the very science fictional realm. But in fact, it's science fiction. There is some science that we can talk about in terms of whether these things are feasible or not. All of the material that you need is going to be on the course website. I've started populating that as of Sunday, so you should be able to see the syllabus up there. There's a course information sheet that you should take a look at because it has a lot of the details about what we're doing in the course. And there's also a course calendar, so you can add that as your Google Calendar if you want, or you can just use it from there. All right, so here are your responsibilities. This is a sort of a long list of what I'm going to be grading on. One thing I want you to notice is that none of these things are an extreme high fraction of your grade. I am not a fan of you have to get an A on your final exam or you fail the course. I think I want to see sort of a broad range of sort of your participation in the class. And so we do have a midterm and final exam, but in fact, they're only 15 and 20% of your grade. Here are the things that we will have. So those of you who've taken a class from me before, you know I do pre-lecture reading quizzes on TED. This is sort of that you're prepared for class when you're coming in, so when we have discussions, you're ready to sort of read it. Obviously, this is the first class, so I wasn't expecting you to be that prepared for it. So we'll be starting these on week 2. But these will be posted on TED, and they're due just before class starts. These are not meant to be tough exams. They're just meant to sort of stimulate your thinking before you come into class. We'll also have in-class participations. The things that you just wrote on are an example of in-class participation, so I'll be collecting those at the end of class. Don't walk out with them, so I can make sure you get a grade for that. But these are just ways to have more engagement in class and sort of get some more ideas out. So they'll be very much like these writing assignments. I may have some other things like it in the class. Now, this is one of the first big ones. So I mentioned that, have you heard about Philae? Have you heard about, you talked about Europa. Have you heard about the Europa Lander that's going out pretty soon? No? Okay. So this is exactly why I want to do this little experiment. This is, there's tons and tons of news happening about space and life in space and SETI and new planets and stuff like that. And in fact, most of the time, I don't even know what's happening because there's so much news out there. So you are going to help all of us learn a little bit about what's happening in the world today in terms of astrobiology, about space, and about planets. And so every one of you is going to be responsible for doing one presentation in class, a very short one-slide presentation, right? Not very challenging, but it will require you to go out, find a news story, and tell us about it, and tell us a little bit about the background of it, right? In addition, you're going to do just a one-page, probably really half-page write-up of what that story was about and sort of how it's relevant to the course. They'll have a little more detail about this on the webpage. But just as a model, just this weekend, I was reading the New York Times, and there was this article about SETI, and it was titled, "Should We Keep a Low Profile in Space?" Seth Shostak is actually one of the, so SETI is a search for extraterrestrial intelligence, if you haven't heard that phrase before. There's actually an institute in California for the search for extraterrestrial intelligence, so that's how sort of ingrained this sort of idea has become. There's actually a building you can go and find scientists who are doing this as a living. And there was a recent sort of conference asking about, should we be letting other aliens know we're here? In the last sort of several decades, several groups have sent out signals to specific stars with radar and radio telescopes. Sometimes they are authorized. NASA has done at least one back in the 1970s. This telescope, this is a radio telescope in Crimea. They've sent like 4 in the last 10 years, and mostly they're kind of like, "Hi, we're a Crimean radio telescope. Come visit us someday." I mean, they're kind of doing this on their own. Because it turns out it's very easy to send radio signals out. We're actually sending radio signals out all the time. When you turn on your radio, you're capturing the signals that are coming to your antenna, but they're also going out into space. And so this article was discussing whether we should be a little more careful about this. Right? We have all this sort of chatter going on into space. How do we know that the aliens that we're listening in, if they are listening in, are necessarily happy aliens? And won't look and see if this is our next meal. Now, my personal feeling about this is that this is a little bit paranoid. We are a little bit paranoid as a culture sometimes about others. We use aliens for different words, not just for people out in space, and we don't usually use it in a very positive way. And so the fact of the matter is we're sending out messages all the time. I actually see no problem of sending messages to specific places because chances are nobody's listening, because as we'll talk about, the odds are very low. But the other side is we shouldn't assume that all aliens are out to eat us. That's sort of something that's still in science fiction. So I'm bringing this up mostly as a modeling example. So this is an article. I'm showing you the primary source. I'm talking about the point of the article, and I'm giving a little bit of my own personal opinion on it. This is the kind of thing that I'll expect for this kind of news reports. Okay. All right. So I've got a sign up form. This is, you can either go here. By the way, these lecture notes are going to be online as soon as the class is over. But you can also go to the TED site, and there's a little link that says sign up for a date. That's just a sign up for a date. If you have an idea of what kind of article you want to do, great. I will sort of ask you ahead of time so we don't have multiple people doing the same articles. But make sure you sign up for a date in the next week, because after that I'll probably just start sticking people into slots so we can fill them in. So you have some choice in the next week. Okay. Next, so we will have some homework assignments. The first one will be posted on Friday. These are just sort of classic take-home homework assignments, although a lot of them are sort of going off and doing some internet research. There's a lot of information out there, so I want you to have a chance to sort of look at and sort of critically analyze it. But of course, we will have some concepts in the class that are related to physics, chemistry, biology that will be sort of covered in the homework assignments. So we also will have a lab activity part of this, and this is what's going to be taking over the discussion section. Now, I sent out this this time to meet link to find a time, but unfortunately, I didn't really know how to use the time to meet thing. So in fact, what all of you did was send me like 30 or 40 individual times that then overwritten every other time. So I actually have no idea what the intersection of all those is. So we're going to do that now. So here's a selection of discussion times that are available. Now is a good time to get out your schedule if you don't have it, or if you don't have it memorized. And what we're going to do is do a vote to see which one of these times is least impacted. Least impacted. So you're not going to vote for a preferred time. I need you to vote for a time that you absolutely cannot do it because you have a conflict. Right? And I prefer that you don't vote because you don't want to do it because you know, I don't like to get up at 9 a.m. on a Friday. You're here now, so you know. But if you have a schedule conflict, that's one we'll have to cover. Okay, so if you're ready, how many cannot do Tuesday 12 p.m.? Many. Okay. How many cannot do Tuesday at 5 p.m.? A non-intersecting many. Okay. Wednesday at 11. Oh, it's gonna be bad. Okay. Wednesday at 1. You guys are busy. Wednesday at 2. Wednesday at 5. Thursday at 12. Friday at 9. Friday at 1. All right, so the only way to do this then is to keep the original time, which is Wednesday at 4. Okay. That's what we're doing, Wednesday at 4. Okay, so I'll send it in. Now, that being said, these labs are going to be great because I've actually got some help from other faculty in sort of designing these things. Some of these labs are actually happening in the lecture itself, so you'll make those at least. And then some of them, because we're two of the labs are actually night sky observations. We're actually going to go out and look at some of the stars and do some exercise with that. Obviously, can't be done at 1 o'clock in the afternoon, right? So those will be after hours. So that's going to include, so we've got, I'm still working on this a little bit. We've got someone at SIO who's going to do a geology tour around the coastline here so we can see some of the sort of rocks and sort of sediments in the history of the Earth just here locally at San Diego. I got someone who's going to, at Birch, who's going to sort of hopefully find someone who can give us a little sort of tour of evolution and sort of the sea environment. So these are kind of just hands-on seeing what astrobiologists actually think about. They're not meant to, you know, make a measurement 50 times, get the standard deviation, blah, 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 kind of right? This is actually kind of get our hands on what's going on. Now, another part of this is, so how many of you have picked up your universe lecture activities manual? All right, a couple of the labs are going to be in this as well. So you want to make sure you pick up this book. It's a fairly cheap book. It's paper cover, it's no black and white, it's not too bad. We're going to do a couple of the exercises in here, and this will also be, some of your homework assignments will be drawn from here as well. So make sure you pick that up. Okay. Now, there's going to be, I think, 6 or 7 of these labs. You only need to make 5 of those, and so if there's 1 or 2 that you particularly can't make because of schedule conflict, it's okay. You've got backups. Okay, any questions on those? All right. So one of the main parts of this course, again, because this is a course that's on interdisciplinary ideas, there's a lot of sort of concepts that we're going to throw around. What I have found in the past is one of the best ways to explore these ideas in detail is to allow you to have a little bit of flexibility to do a course project that is of your own design with obviously some constraints. And so this is a collaborative project, right? You can have teams of anywhere between 1 and 3 people. The larger the team, of course, I'm going to expect sort of a larger amount of total work, but you guys will decide how to break that up. The project has to be based on the course concepts. There should be at least 1 primary scientific source, and I'll have a workshop sort of mid-quarter on how do you know what's a primary source, because I think that some of you may not have actually worked with primary scientific sources yet, so we'll talk a little bit about that. And it must include a creative component. So I'll show what examples of that in just a moment. This is how we're breaking it down. You're going to have, so our midterm is week 5. Right after that, you'll have a project proposal, which is just a paragraph in a short bibliography to kind of describe what kind of project you're doing. Mostly that's so I can tell you whether it's a feasible project. I often get project requests that are like, I'm going to write a science fiction novel in the next 3 weeks. That'd be cool, but it might be a little hard and probably too much for 20% grade. The final project itself is a 3 to 5 page write-up, and any materials that are associated with the creative component, which is in week 9. And then everyone will be required to do a 5-minute presentation just on what they explored and any aspects of their creative project. By the way, notice that you have a presentation for your news report, and you have a presentation for your project. That design is purposeful, right? So the news report is kind of a warm-up for doing the project presentation. And this will take place in the last week of classes. Now, here are some examples of projects that have done well in the past. This is just sort of a laundry list. Some of them are very sort of science-oriented. For example, if you're very good at computer simulations, you can do maybe simulation planet orbit. So someone's already done this, so you have to think of a little bit slightly different thing to do. We have had students actually do research projects with some of the folks here in the astrophysics department that work on some kind of astrobiology, somewhat related topics. And so you could do kind of a mini project with them. And then there's other more creative things. I had a wonderful original song about moon phases, which maybe I'll play at some point. I had a great movie of a dance interpretation of planet formation, which I'm still trying to understand. Actually, this was from last year, this novel card game. Someone produced a card game on how you get a habitable world, and it was completely addictive. Yeah, I had to put that away for a while. And this was a fun one. Someone actually, so these are the Galilean moons as cookies. They're about this big. I'll bring them next class. And they are actually their density profile is the same density profile as the moons, which was made with like different materials and stuff like that. I'm not going to eat these because they're super sugary, but the idea is just to be as creative as you can, but also to adhere as much to the scientific aspects of the project that you're thinking about. All right. So again, this was, if someone just gave a couple balls that were colored nicely, that's probably not an A+ project. But the fact that the student thought about how does the density profile change inside and how do I build that in, that was a really interesting project in that sense. So you want to sort of hear both the scientific and also creative impulses. If you're afraid you're not very creative, that's okay. I'm not very creative either. So you can do something that's a little more straightforward, and I'm happy to work with you on sort of helping you design a project. And remember, you can work in teams up to 3. And so, maybe if you find a good programmer and a good creative person, you can come up with something that's pretty spectacular. Any questions on the course project? Okay. So again, you should be thinking a little bit now about what are some things I'm interested in this class, and maybe I can design a project around there. But you don't have to really design this until after a midterm. So this is something you should be thinking about now, but not necessarily doing too much work on. Okay. All right, and then the last thing is we will have a couple of tests. There's a midterm exam on the week 5 Thursday. That's going to cover the first 6 chapters of our textbook, which is right here, which is kind of beaten right now. That's basically covering up into sort of life on Earth So we'll talk about the universe and life on Earth. And then we'll have a final at the end. And we're actually scheduled from 8 to 11 a.m., but I don't think anyone thinks at 8 in the morning. And so we're going to have that just a 2-hour final, so it's going to be a much smaller final than it had in the past. Think of these as kind of 2 midterms. The second midterm is really covering the second half of the material. The focus of these tests are really on the concepts. There will be some mathematical problems that we'll talk about in class and maybe on the tests, but the idea is really thinking about the concepts and the ideas that we're covering. And the questions, if you've taken my class before, or one of my classes before, I really kind of give you the questions as much as I can beforehand. So in your homeworks, in your reading quizzes, in the stuff that we do here in class are usually the sources of where I draw my questions from. Okay, this is the grading scale. There is no curve, but there will be a possibility for extra credit if you're worried about your scores falling behind in some way. In fact, the first extra credit assignment is tomorrow. I'm also teaching a class appropriately named Are We Alone for Cat 3. And we've gotten Richard Dreyfuss to come and host a screening of Close Encounters of the Third Kind. Who's seen this movie before? Oh, good. Well, you're in this class, is probably why. So we're going to have a special screening of this at the Atkinson Theater, which is over in Warren College. However, it is completely sold out. It was sold out like the first day because of Richard Dreyfuss. And so we've organized to have a special screening on the same day, on tomorrow, Wednesday at 7 p.m. at Center Hall 101. So you should, if you can't make this, which I can't even make this, you could go to this one. And if you write a 1-page reflection on this stating 3 assumptions made about alien life in this movie, I will include that as a 1% extra credit. So we'll have a couple of these assignments. This is due on Thursday. Turn it on the TED site. There should be an assignment now posted that's a turn it in for that particular assignment. Okay. So this is an opportunity to sort of go out and watch a movie and think a little bit about the concepts of this course. And we'll have a couple of these through the quarter. Yes, ma'am.
The PowerPoint's gonna be on the TED, correct?
Yes. Yeah. So yeah, I'll also put an announcement about this on the site. Any other questions? Okay. All right. The Riot Act. So remember that we're, UCSD, we have an integrity policy. These are some of the things that are big no-nos for this integrity policy. As part of this, I have everyone sign an integrity pledge, so we're going to do that now. So go ahead and pass around that way. Pass around that way. Pass around that way. This is a simple statement just saying that you understand the integrity policy and you promise not to turn in other people's work, right? That you won't copy and stuff like that, that you'll actually put effort into the assignments and turn in your own work to use. Plus, you'll give me your first child. Just kidding about that. Okay, while you're reading the fine print and sign your name, any questions about the course structure? Crystal clear. Yes, sir. Yeah, it'll be based on the reading quiz will be based on the material we're going to cover in the lecture right after the reading quiz. It'll be mostly based on material in the book. I will occasionally assign some extra reading because, to be honest, this is a pretty simplistic book. And there's much more interesting things out there. So I will have some sort of maybe snippets of reading, and that might be included as part of the reading quiz. But you'll have those in advance. Any other questions? How many of you are taking this for a college requirement? Wonderful. How many of you are taking this because you think it's super cool? That's okay. You didn't raise your hand. That's okay. I'm not going to mark you down. Okay. How many taking this because you're a physics major? Wow. Okay. I always have one. That's good. All right. Okay. So last little bit here. Just to get a little more structure to this. The astrobiology as a research subject is fairly new, and it's something that your tax dollars are actually paying at some level. This is a major endeavor part of NASA. Because it is one of these sort of foundational questions that we have about, our existence. Where do we come from? And so NASA has actually developed this astrobiology roadmap, and I'm just going to flip through this real quickly. But these are sort of the big questions that it's asking for: searching for extrasolar habitable planets. Right, that's the key distinction we'll talk about in a little bit. Searching for life in the solar system, discovering the origin of life here on Earth, examining life and its environment, both the environmental impacts on life, but the life's impacts on the environment as well. Many of you probably know that we're going through a great experiment right now where we are releasing lots of carbon to the atmosphere. We're going to see what happens. There you go. Measuring the limits of life. What are the extremities of extremophiles? We'll talk a little bit about that. And understanding the future of life here on Earth and elsewhere. And then detecting signs of life, not just in the solar system, but also throughout the universe. And let's see what we got here. Okay, I'm actually going to skip these. A little bit too details. These will be on your notes. Now, so this is a multi-year, multi sort of thread process. It touches on biology, space science, chemistry. There are literally thousands of scientists around the country who are working at some level of aspects on these questions. And so how much do you think this costs? And guess how much it costs per taxpayer? Per taxpayer. Any guesses? Less than half a penny. Less than 1 cent. Okay, any other guesses? I'll take 2 more. I'll take 3 more. Yes.
I'll go with like $300.
$300?
Yeah.
$300 per taxpayer, okay? 2 more.
$150.
$150. This is like, I didn't give the answer away. 1 more.
$1.
$1. Okay. So this is back in 2008. Most recent money I have. About $40 million was spent on the National Astrobiology program, which again sort of funds many, many different scientists. It actually funds 15 whole institutions. Right, not big institutions like UCSD, but like kind of 100 to 150 scale institutions of people working together. When you divide it, 15 cents a year. So 1 penny got it. Everyone else was over. Right, it's pretty cheap, but the actual impact, if anything comes out of this, is actually pretty profound. Not just this sort of a philosophical idea that if we find that there's life in the universe, we're not the only planet in the place that has any kind of life forms. But think about sort of the how much money the sort of biotech makes today, right? Things like drug discovery, things like also I'm not even sure what biotech does today. But imagine that you have a whole new system of life that you can sort of tap into. So there's a lot of sort of really interesting things about whether we could find not just different life forms, but maybe probe a little bit into the origin of our own life forms. If we find life out there that's very similar to us, that suggests that really is maybe one path for life, and it's a very common path throughout the universe. If we find it's completely different, first we'd have to recognize it, which is a whole other problem. But then we have to ask, what other ways can life originate? What other materials can life be made out of? What other environments can life originate out of? And that can open up a whole bunch of other questions. Okay, so that's it today. I'm going to end a little bit early. Make sure you turn in your writing sheets and your integrity documents. And I will see you on Thursday